Welcome to EDU World Space.
All right, so to begin this question, we must first take a look at the information that we've already been given. So we already know the linear charge density, which is 5 times 10 to the negative 12 coulombs per meter. We also know the mass, which is 1.67 times 10 to the negative 27 kg. We also know the charge, which is positive 1.6 times 10 to the negative 19 coulombs. And finally, we know the velocity, which is 1.5 times 10 to the power of 3 meters per second. So to calculate the proton's initial kinetic energy for part A, we know that the equation for kinetic energy is 1/2 mv squared. So and if you just plug in the values that we have, so it's 1/2 times the mass, which is 1.67 times 10 to the negative 27 kgs. So let's keep it in standard units. Negative 27, to the power of negative 27 times the velocity, which was 1.5 times 10 to the power of 3 squared. And this whole thing is squared. So now if you just plug this into a calculator, if you could just give me a second to plug this in. Ten to the power of 3, the whole thing is squared. We get that the kinetic energy is 1.879 times 10 to the negative 21. Yep. And we cannot forget our units, which are, of course, joules. So now if you move into part B, so if you say the maximum distance a proton came close to the charge must be x, so let's just say this is the distance, so let x equal distance. So if you do that, now we can formulate a little expression to find out the maximum distance. So the potential energy is 2 times k times the linear charge density times the ln of 0.5 over x times the charge. So let's just get that potential energy is 2 times k times the linear charge density, which we know is 5 times 10 to the negative 12 coulombs times ln of 0.51. Actually, it is the distance. So the distance in this case, it is 18 centimeters. So it's 0.18, not 115. 0.18 over x, which is the distance that we set before, times 1.6 times 10 to the negative 19. Yep. So now if you just substitute the value of k, which is 9 times 10 to the power of 9, and we plug this whole thing into our calculator. So if you just substitute this as 9 times 10 to the power of 9. So just once again, this is a standard equation that you'll be using for potential energy. So you should have this equation with you at all times. So so you should have a reference to this equation with you all times. 10 to the power of 9 times 5 times 10 to the, hold on, I'm just putting it into my calculator, times ln. Yeah, so before we actually put this into our calculator, we know that we need to solve for the variable x in this case. So by the conservation of energy, we know that the initial energy is equal to final energy, and we already calculated the initial energy, which is equal to the kinetic energy. So theoretically, all of the kinetic energy should have turned into potential energy in an ideal scenario where no energy is lost. So this whole expression is equal to the kinetic energy of part A. So now if we isolate for the variable x, we can solve this equation. So I've actually already gone ahead and solved it for us, since this is a very algebraic dense equation. So x is equal to 0.1558 meters, and that is the maximum distance that the proton can get as close to the charge as possible. So that's it for this problem. Hope you learned something, and thank you.